Standard 6.9. Solve exponential equations using logarithms, including those in application problems. Alright, so we have our first exponential equation here. Our job is to solve for x, and we want to isolate the part that has the exponent on it. So we're going to isolate the 5 to the x minus 4 power first, and we can do that by subtracting 3 from each side of our equations. We have 5 to the x minus 4 equals 9. Now 5 and 9 we cannot rewrite as a common base, because if we could rewrite it as a common base, then we could set the exponents equal to each other. But in this case we can't rewrite it as a common base. And x is trapped up here as an exponent. And so what we want to do to untrap, I guess, from the exponent position is to use logarithms. So we're going to rewrite this as a log equation. Log base 5 of 9 equals x minus 4. And that is our strategy always for solving an exponential equation. When your exponent is up here in that, when your variable is up there in that exponent position, what you want to do is to rewrite it as a log equation. So we have rewritten it as a log equation. And now we want to evaluate what's log base 5 of 9. Now some of you with the newer calculators, you have a log button under the math menu. Those of you who have older calculators, we have to use a change of base formula. And to evaluate log base 5 of 9, we evaluate log 9 over log 5. So on our calculators, we're going to do log 9 divided by log 5. And we get 1.37 approximately. And to finish off the problem, we add 4 to both sides, so x equals 5.37. Again, the big idea is get the exponential part alone first, convert it to a log equation, and then evaluate. All right, so let's look at a similar type of problem, but in an application context. So we have a population of bacteria. It's growing according to the given equation. And we want to know how many bacteria were in the initial population and how long before the population reaches 5,000. So for the initial population, that is when t is equal to 0, right? No time has passed. Initial means your starting value. So if we evaluate this at t equals 0, we could put 0 in for t, which is 80 times e to the 0, which is 80 times 1, which is just 80. So our initial population of bacteria was 80 bacteria. And then we want to know how long before the population reaches 5,000. So 5,000 is our ending value. We're going to put that in for y. And we have to solve for t. So let's divide both sides by 80 first. And that's 62.5. And we're doing that because we want to isolate the part that has the exponent on it. The e has the exponent, we want to get that e alone. Alright, so now we want to solve for t, but t is trapped up here in that exponent position. To bring an exponent down, like in the previous problem, we want to use logs. So we're going to rewrite this as a log equation. It's log, our base is e of 62.5 equals our exponent, 0.07t. And log base e is the same thing as natural log of e. So natural log of 62.5 equals 0.07t. And then finally, to solve for t, we can divide by 0.07. So natural log of 62.5 divided by 0.07 would give us our answer. And our answer is about 59 months. So we'll write that here. T is approximately 59 months. And in about 59 months, we will have close to 5,000 bacteria. So again, this standard is 6.9, solving exponential equations. The big idea is to convert to a log equation to isolate